Okay, so end of frequency response, we get through this today. We finished lab 4 on Friday. If you need some help with anything, I will be available. I've told too many people that I'm pretty much done, so I haven't gotten any work done. I was just going to post the practice exams this week. I have not managed to do that because I told one too many people, oh, I have nothing to do. Oh yeah, just come in my office. Well, let's just have meetings for stuff we're going to do over the summer. Okay. So we'll finish lab 4 this week. Homework 10 will be due next Tuesday. I've already gotten a few good questions on that one. I'm not going to, okay. And then the lab 4 quiz will be next Friday. The following Friday, there's no lab. Nothing's due. I will take, up until this day, I will take 1 week's worth of lab late for full credit. So either like lab 1 or lab 2, or half of lab 3, or a quarter of lab 4. Last homework is Thursday, April 22nd, and then we have the final exam. Okay.
Are they shorter homeworks then, 11 and 12, or just 12? Right back to back?
They're back to back. That's because I had to like get them in. What is homework 11 on? Homework 11 is the last frequency response homework. You could probably actually start working on that now if you wanted to. I just put a week in between them. Homework 12 is over the ADCs and DACs. And I think both of those have a reasonable number of bonus homework points on them, at least like 20. One of them may have 50. Where you can get like a 120 out of 100. So if you want to pull your homework score up, there's an opportunity there. And of course, the course evaluation is worth points on the final exam. So send me a notification. It's like 5 points on the final for free. Send me a notification that you finish it, and I will give you 5 points. And there is a practice final exam that's worth a variable number of points. Exam points. I just add it to the final exam grade. So if you do that, I mean, it will and the final exam is in the same category as the other ones. It automatically like boosts your average up across the board. I just have to look at what your actual exam averages are and see how many points I want to give you. It's been worth as many as 30 and as few as 10. Just because I don't want to give everybody A's. I don't care anymore. I did do that once. I gave everybody in the class an A, but it wasn't here. I don't know what's going on with 639 and 638. It may or may not be taught next fall. It may be taught over in the math department next fall. Cryptography, that's a possibility. Looks like mixed signal design is on the books. If you want to take 490 in the fall, sign up for it. There is nobody enrolled right now. We need to get probably at least 10 people in there or they'll cancel it again. That's a fun class if you haven't taken it. We actually go and it's more like how you build things. And it's more from a printed circuit board standpoint. So even if you're a power guy, it's a good elective, just a different perspective than on how to build things other than what you get from Dr. Yarmalasu. A lot of reading data sheets. Last semester, we were like all pretty much virtual, so it was a lot of simulations. I kind of liked having that component in there. There were multi-sim simulations, though. They're easier. I like having that component in there, but I want to get back on the bench and have people actually measuring stuff, triggering oscilloscopes, and learning how to use the test equipment better than what you learn in 188. Device physics is also on there. It's taught by Daphne Chen. I call that my elective because it's kind of like my field. And that's what I'll be doing next semester. Let's see, what else next? Frequency response. I put this in here as a reminder. I added this into this set of slides today. These are the summary of the amplifiers we've looked at, and their input resistance, their gain, and their output resistance at mid-band. Because we'll be referring back to this occasionally. I don't want to go through and rederive these. I just want to look them up especially when we look at the common gate. You know, what's the input resistance? We'll just say it's this. I'm not going to do that again. So we'll go through and we'll use that occasionally. We're looking at the high frequency band. We want to find the point where the gain starts to roll off. We usually don't want to use the amplifier at frequencies greater than where the gain starts to roll off, because we get a lot of nonlinearities there. This is a summary of what we did in class yesterday. This was for the common source amplifier. It's going to turn out it's the same answer as for the diff amp. So we're not going to go through all that again. We're just going to say it's the same because it looks like a, oh, we'll get there. So they're pretty much the same. The big things are you can kind of look at these equations and get a handle of what you can reduce to reduce the time constant. And if I reduce the time constant, I'm going to increase the frequency response. The high frequency cutoff point is going to be 1/2 pi times the sum of all the time constants for the individual capacitors. And what we did is we looked at the individual capacitor, found the equivalent resistance it saw, and found the time constant associated with that, multiply R by C, and did the same thing for the next capacitor, found its equivalent resistance, and the third capacitor. However many capacitors you have to do that each time and add them all together, and you'll get the total time constant. And if you have to guess what your frequency, where your frequency cuts off, 1/2 pi RC. 1/2 pi sum of the taus. I think that's the biggest, most important thing that we have to get, especially for the final. We want to look at the cascode and the common drain. The common drain in your textbook is referred to as the source follower. I just caught this one recently. It's the same thing because the reason why we call it a source follower is because it has a gain of approximately 1. The common drain is I know exactly what's going on. A common drain has signal ground on the drain, the inputs on the gate, and the outputs on the source. And it pretty much automatically turns out that the voltage on the output is the threshold voltage minus the gate. But they follow each other. If the gate voltage goes up, the source voltage goes up. It's used as a buffer amplifier. Increases the current capacity of the device. So again, this is what we're looking for is FH. And I should shut up because I have a bunch of slides to go through. Now these parameters are used for all these circuits. Same ROs, same GMs, same capacitance values. What you can do and what I recommend when you're calculating these is go through and first thing, calculate R sig prime. You're not given RG in this case. So it would be R sig in parallel with infinity. This would just be 100K. You could go through and calculate RL prime. It is going to be a number. It's going to be RO, whichever RO is that you need, in parallel with RD, in parallel with RL. Then go ahead, once you get the RL and the R sig prime, you can calculate CN and CL prime, and then you can go back to those equations that I showed you right about here for the common source or whatever one you're doing, and calculate what the time constants are. It's somewhat tedious, and thank goodness computers do this for us, but this gives us insight into how things work. Okay, so for the common gate, if you have a discrete circuit, you're using resistors out of the parts cabinet. RL is going to be much smaller than the RO of the transistors, so generally you can neglect RO. If you're inside an integrated circuit, you can't neglect RO because RL is the RO of another transistor and they approximately equal each other. So this is, yeah, another thing that you can throw in there. Depending, okay. So this is a hand-drawn version of a common gate amplifier. And since it's a common gate, remember our gate is an AC ground. So we're going to look at this. We're going to use the OCD method. We're going to ignore CSB because it's small, so we can take this one out. We're going to ignore CDB because it's small. We can take that one out. And if we look at this, if we can find capacitors that are in parallel, is this the one? Oh, never mind. If we can find capacitors that are in parallel, we can add them together, and then we only have to find one equivalent resistance. So like here, CL is connected to the same node as CGD. The other side of CL is going to ground. Since this is an AC ground, we could take this one out and make this CL plus CGD. One less time constant to do. Okay. CGS is going to be a significant one, so I need to find that one. CGS is going from R-sig, basically R-sig to ground. Now, is this the really horrible one? No, not really. What I'm going to see here, CGS, if I'm looking in here, the equivalent, and I get to okay, this is like, I'm finding the Thevenin equivalent resistance at CGSCs. So I take out CGS, and I have, my gate is at AC ground, and my CGS is right about here. I need to find the equivalent resistance looking into R-sig. Yes, I know. Yay, or, and this is a RL. RL. I need to find the equivalent resistance, and I get to take the capacitors out too. So I need to find for CGS, I'm going to call this RGS. And RGS is the equivalent resistance that CGS sees. It'll be looking in right here. So I have R-sig in parallel with the resistance looking into the source of the transistor. And remember that chart from exam 2? That is R-sig. Looking in there, I have 1 over GM times 1 plus RL over RO. So this is my RGS. Okay. And RG and RGS.
So in this case, with this is being a DC drawing of the circuit or an AC?
That's an AC drawing of the circuit.
So with AC drawing, we want to find the gate source resistance there. We just keep those two drain and source branches.
Those drain and sources as in parallel. Wait. So the gate to source, I don't know what you're saying right now. What I'm doing is the gate to source capacitance was right here, right? But this is an AC ground. So I could just have taken it and moved it here. Because it's between, this is CGS. Is going from the gate, is going from the source to ground. Because the gate's at ground. Okay. And then I find the equivalent resistance where that CGS would be. And so that CGS is right here. So I have to take into account that that equivalent resistance is, I could go through the path. I have a parallel R sig with parallel looking into the source of the transistor. Okay. And this is the AC model. Now, I got rid of one capacitor here by just putting those in parallel. CL and CGD, what we said was those two are equivalent. So I'm going to change this a little bit so I don't have to draw 3 circuits. 2 pi CGD plus CL times, I'll just call it RL because it's shorter, plus RGS CGS. So I got one of the time constants. We need the other one. I need another in parentheses there. Okay. So to get the other one, I've got to find the equivalent resistance looking into this node right here. That should be grounded if this is an AC model. So looking into this node right here, I see the equivalent resistance associated with this capacitor is going to be RL in parallel with the resistance looking into the drain, which is from our chart, RO times 1 plus GM times the resistance on the source, R sig. Add up the time constants, multiply by 2 pi, flip it over, you've got the frequency response. Okay, that one wasn't too bad. That's all we're going to do on the common gate. Okay, we plug in numbers to figure out what this is. The first thing you have to do here, of course, is you have to calculate what RGD is. And RGD is this big mess. RL and parallel. So we have to calculate that. And this is basically the big RO of the transistor. This piece of it is big RO. So it's RL in parallel with big RO. RGS is R sig in parallel with RN, which we've actually found right here. That's the input resistance of the common gate. And we could go through, calculate all those and figure out what it is. If you want to follow along, and if I gave you, I think I gave you the common drain on the homework. But you could, the details of the calculation are in the slide solution. And it's kind of tedious right here. The RN of a common gate, is that part? Yeah, never mind. It comes in. And when we calculate this, it's just a big tedious calculation, plugging in a bunch of numbers into a bunch of formulas. Do these first. FH comes out to be 10.2 megahertz. What we were getting from the last class, the common source, using these same parameters, these same transistors, we were getting like 25 megahertz. So the common gate doesn't have very good frequency response. Not used a lot except for in a cascode. Now for a cascode, my input comes in off the gate. It has to get to the drain of the first transistor. So this is a common source. It comes into the source of this one and has to get to the drain. So this is a common gate. Not expecting very good frequency response out of it because you got both of those amplifiers and they'll probably be dominated by the common gate. Another problem is it's got a higher gain. Looking into the Q2 drain from our chart would be RO2 times 1 plus GM2 RO1. So that would be the resistance looking in right there. If you look at this, for this two-stage amplifier, there's a whole bunch of amplifiers. There's a whole bunch of capacitors. I've got 6 capacitors on here. This would require 6 OTC thingies. We don't really want to do that. What are we going to do? We're going to see where do we have things in parallel. Well, CGD2 is from the drain to ground, and CL is from the drain to ground. So I could just make this CL plus CGD2 and make this one go away. CDB1 goes from this node to ground, and so does this capacitor. So I could just add CGS2 to that one and get rid of that one. Now we've reduced our capacitive load by down to 4. Is that, did I catch them all? Yes, I caught them all. Yeah, okay, I did everything on that one. And yeah, I don't know what the slide's about. It makes it, just so it says this parrot has ceased to be. It was supposed, I don't know. It's left over from Dr. Brower. I quizzed the 280 students on this for extra credit on their exam. I'm sure that she used to actually have test questions that were worth real points on these slides. Okay. So we're not going to do this. Yeah, is this the one we don't get to? No, we don't. So we could take, one of the 4 capacitors. This is CL plus. Did I freeze? No, I didn't. I just lost my pointer thingy. Plus CGD2. We could take that one here. And find the equivalent resistance that it sees. It would with all the other capacitors open. Its equivalent resistance would be RL in parallel with RO2 times 1 plus GM2 RO1. Approximately equal to RL. So we're basically just doing the same thing over and over again. They go through that in the book. And then we'd have to find, if we wanted to find, and this is the process, I want you to understand the process more so than have me sit here doing these calculations over and over again. If we want to find the time constant, I find the capacitor, the equivalent resistance that it sees, and I add up all of them. In this case, there would be 4 of them. And if I want to find the high frequency bandwidth, it's 1 over 2 pi tau h. The total tau. The sum of all the time constants. This works with any circuit, not just amplifiers. If you can find the biggest, fattest capacitor on the board, this is going to be the one that probably dominates, as long as and you can always estimate it by just using the biggest capacitor you have. That's a good place to start. It works for op-amp circuits too. When we compare the common source and the cascode, pretty much what we find is when I build a cascode, I increase the gain. And I'm increasing the gain by some factor A0. Remember, because I'm basically increasing the output resistance. So this increases the gain by some factor. When I look at the bandwidth, what happens is the bandwidth decreases by that same factor. So anything you do, and this happens universally, anything you do to increase the gain of a circuit is going to decrease its bandwidth. So gain bandwidth product. Usually not listed on data sheets, it's usually listed as the unity gain bandwidth. Unity gain bandwidth, which is the bandwidth when you have a gain of 1. And if you want to find the bandwidth when you have a gain of 10, you just divide that by 10. So you have to increase the bandwidth you're looking for on there. Right. And if you take the cascode, and this is kind of like the interesting effect here. This is the regular common source amplifier. It has a lower gain, but then the bandwidth starts to roll off faster. And if I have the cascode, it has a higher gain. The bandwidth rolls off earlier. And for both of those, they intersect at unity gain bandwidth, which is our 0 dB level. Okay. The common drain is also called the source follower, and I believe Cedric Smith usually refers to it as the source follower. For the BJT version of that is the emitter follower. So we want to put our capacitors in here. Our high frequency capacitors are going from the gate to the source. They're going from the gate to the drain. C, gate to drain. And C, source to body. So that would be just going, that would be source to body. Body's usually ground. So I could just add that one in here. So C, source to body, could be added in there. 31, is it small enough? It's generally, well, it depends on what region you're in. Remember, CDB. Yeah, those are the 3 that I care about. That one's shorted to ground, CSB, CL. CSB, those 2 are in parallel. That's exactly what I did. Okay, why not CDB? Where's C, drain to body? Oh, this is an AC ground. So C, drain to body, is going from ground to ground. So we don't need that one. So we can combine these 2. We're left with 2 capacitors, I believe. I think I missed one. CGD, CSB, CL, CDB, CGD, CG. No, I got 3 capacitors in there. Yeah, I got the right number. I know the answer. Okay. So for this common drain, this is our goal here. It has a 0 at negative GM over CGS. We want to find tau H, which is the sum of all the RCs. This is a reminder not to do that. If we calculate the 0, where's the 0 going to be at? We take our GM value, we divide it by CGS. Our 0 comes out to be 11.7 gigaradians per second. If I can get a single transistor amplifier operating at 11.7 gigaradians per second, I'd be a hero. It just doesn't happen. MOSFETs, you can usually get last time I was trying to do this, it was like 100 megahertz or something like that. They're not that fast. Okay. The reason why I'm reminding myself not to do this, it's the same concept. We take each capacitor and we find its equivalent resistance that it sees. We add all those together, add all the time constants together, and we take 1 over 2 pi tau total. It's already done for us. This is the circuit I'm starting out with. So I want to find CL. So for the CL capacitor, I'm looking for the REQ where CL used to be. And I'm going to call that RCL. So the REQ it sees is RL prime. In parallel with looking into the source of a transistor with its drain grounded, I go back to the chart. That's 1 over GM. It would be 1 over GM times 1 plus RD over RL, but RD 0. So it's just 1 over GM looking into the source. So I calculate my tau CL. It's going to be whatever my RCL is times CL. Then I go move on to the next capacitor, and this is going from the gate to drain. So this is where the capacitor was, and I open up everything else. Looking this way, I see R sig in parallel with infinity, which is R sig. And looking this way, I just see a short to ground. So it's just R sig. That's the equivalent resistance the gate to drain sees. Then I calculate tau GD is just RGD times CGD. You don't have to, you can just look at the formulas in the book. You don't have to go through and do the OCD stuff if you have to. Now this is the tough one. We want to find RGS. And I put in that T model of the transistor. I put in a test source here for VGS. And I want to calculate VGS over whatever this test current is. That will be the equivalent resistance. I have to do a little bit of circuit analysis, and that's where this formula comes from. REQ is R sig plus RL prime over that. I calculate its time constant. It will be RGS times CGS. And yeah, go ahead, please. I feel like I've been doing a monologue.
Why does this model have a gate to body?
A gate to body.
Isn't that like the only question you put in there on purpose?
Let me, no, it's, well, oh. I can actually answer this question. Okay. We're operating this transistor in the saturation region. Okay. In the saturation region, when you're in cutoff, the gate to body capacitance is big. It's the entire MOS capacitor. When you're in saturation, most of that capacitance gets split, that capacitance gets split between the gate to source and the gate to drain, and none of it's going between the gate and body. And so that's why in saturation, the gate to body capacitance becomes negligible. Wow, I just impressed myself.
Wait, so then when it's
Yeah.
triode, since it's like half and half?
In triode, it's split, yeah, pretty much equally, half and half. And in saturation, I think 2/3 of it is through the gate to source. CGS becomes bigger than CDB. It's all those capacitances vary. And then I'm just going to have to turn around and become, never mind. So we do the calculations, we go through and we find out, ooh, look who won. Who won the frequency response game? Common drain. That's wonderful, but how much gain can I get out of a common drain amplifier? Yes, exactly. Not much gain, but this is a good high frequency buffer. This is the workhorse that these two are the workhorses for gain. And the frequency response is kind of killed by the Muller effect. If I want something, I have seen high frequency MOSFETs with gain out around 50 to 100 megahertz. But you can't use them for an amplifier like in a Wi-Fi system. That's like gigahertz. You have to go into BJTs and things like that. And what we did there are radios operating in the 100 megahertz range with FETs. There are techniques you can use to get around that a little bit. You can split the power up so you have lower gain and then a lower gain, and then you get a little bit more bandwidth, and then you recombine the power from all the signals. It's hard to do. BJT, the transistors we actually used in the 1 gigahertz band at Motorola were not MOSFETs. There's something called MESFETs, metal epi semiconductor field effect transistors. So instead of having an oxide layer, they grew an epitaxial layer, and the capacitance of that was lower, so the Miller effect wasn't quite as bad. And then they used, oh no, he was talking about JFETs. I have time. The J word. Back in the dark ages, before they could build MOSFETs, there's this thing called a JFET. They couldn't build that gate oxide. They couldn't build that gate capacitor. So they built these things like this. And yeah, he still brings up that word, and I just call it the J word. And then he looks at me like I'm. They have really high input resistance. Let's put it that way. And then they put a PN junction here. And in order to turn this thing on, you basically, I don't know how the physics of this works because I never did that, but you put a PN junction here. And if I want to turn this thing on, I reverse bias. So this would have to be the P side. I reverse bias this diode and I create a depletion region through here that I can, that acts as my channel. The problem with them is you have to turn them off, and if you put the wrong polarity voltage across the gate to body, you basically have turned on a diode, and they blow themselves up. I'm really expert at blowing up JFETs. Let's put it that way. They have really high input impedance. You'll see them in. If you're buying op amps, sometimes they'll brag about having a JFET input. And if you look at the input resistance, it'll be like tera ohms. So if you need that, they're good for that, and they're good for some other things, but it's been so long since I thought about JFETs. I should do that. Talk about JFETs in 490. So we want to look at differential amplifiers, and the good news is my differential amplifier looks like this. This is the actual circuit. If I draw the AC model of this, this is a current source, so it goes away. This becomes like a virtual ground, and I can separate it into two differential half circuits that look amazingly like a common source amplifier and a common mode circuit, and we'll talk about what happens to the common mode rejection rate. So since this looks like a common source amplifier, the frequency response looks like identical slide to a common source amplifier. We don't have to do that again. Okay. Capacitor equivalents. The capacitors we have on the board, the CC1, CC2, CC3, whatever they're called, these are my coupling capacitors. At low frequencies, we treat them like they're open. We also treat the transistors like they're open. When I get into the mid-band here, most of the calculations actually treat the transistor capacitances like their ZC, 1 over J omega C. And these become shorts. And at high frequencies, all of them become shorts. It all depends upon like the size of the capacitance. Oh yeah, you're gonna do this. I was tempted to just delete these. Okay. We want to see what's going on with the common mode, what happens to the common mode gain as a function of frequency. And what happens is you get this 0. And the 0 is at the input resistance, the resistance of the current source times its capacitance. It's RC, is right where that pole is at. It's actually at 1 over RC because that's not in standard form. So we wanted to sketch the Bode plot of this. This would, if I put this in standard form, it'd be 1 plus S divided by 1 over RC, RSS, CSS. So what I would get is I get a 0, and zeros float, and it goes up, and the frequency that that's going to happen at is 1 over RSS, CSS. So the common mode, we want the common mode gain to be small. When I get above this break frequency, it's going to get big. Now the differential gain, this is a common mode. The differential gain is going to look like this. It's going to be higher here, and then it's going to hit some frequency out here, where wherever FH is, that I start losing it. My common mode rejection ratio, which is the ratio of these two, is actually going to get worse faster than the gain of your amplifier rolls off. So you may have, it's harder for an amplifier to reject high frequency noise than it is to maintain the gain. And there is a slide for this, yes. This is the differential gain. It looks as we expect it to. The common mode gain starts going up here. So the common mode rejection ratio, since it's AD over A common mode, if A common mode's getting bigger, this number's getting bigger, my common mode rejection ratio is going down. It starts going down before the gain goes down. Your amplifier is not as good at rejecting high frequency noise as it is at amplifying high frequency stuff. So this is why we want to use common mode rejection. And this is just like a magic, yeah, I know, even Dr., yeah. Magic, that I didn't write that down. That did not come from me. Okay. I have power supply noise. It's on VDD. And I use that power supply to power my diff amp. Now, since the voltage here at the output is VDD minus whatever the current is through here, IDRD, I over 2 RD. This has had all the noise that's on VDD ends up on my output. So my whatever noise I have on my power supply is going to get on my output. One thing you can do is filter this and put a big cap to ground here, and highly recommended. And I yell at you, you don't do that in the lab, or I just make you do it is what I actually do. I don't yell at you. So I get whatever noise is on the power supply gets passed to this output here. Now, stage 2 magically has a better power supply. It has no noise on it. But if it has a power supply with no noise on it, and I put this noisy signal in here, the common mode rejection is going to make the noise on the output smaller than it is on the input. So we really want to have that around. We really want to filter our power supplies and not have them look like that, but sometimes they do. And something to think about if you end up being a power supply designer, there's a lot of General Dynamics down in Scottsdale, when they hire people from NAU, they almost always hire them to do their do the power supplies for their boards. And then if you're good, if you want to do something different, you want to move on and do something different, then you end up like being an RF engineer or doing something else. But that seems to be the entry-level job at General Dynamics. And the thing is, you just got to make this better. If you're interested in something like that, take Dr. Yermoss's classes, and 490 in the fall. We need to get a few more people in there so I don't have to teach 110 in the fall. That's stupid. I have no idea. I looked today and it looked like there's either 0 openings or there's 0 people signed up. I can't, yeah, what? It could be both. Yeah, you're right. They do that to me sometimes. They set the class limit to 0. I will look at it more carefully tomorrow. I just saw it was on the schedule. Okay, so we got our differential amplifier with the active load. Just a reminder, this is part of the differential pair. Yeah, this is the current source. It's not a mirror. This is the I source, and this is an active load. Part of this. And we looked at this before. Was there a point to this or not? I don't remember. If I want to plump all the capacitors together, why am I doing this? I don't know. I don't see the point of the slide right now. I could. Okay, never mind. I don't want to. Okay, it's not okay. Oh, this is important. CC is about to be revealed. Oh, thank goodness. Okay. So CC is this capacitor right here. You've seen it before in this 2-stage op-amp schematic. This is stage 1 is a diff amp. This was on a lot of people's exam too. Stage 2, my output, my V out comes right here. Is a commons. Did they really do that? Is a yeah, it's a common source amplifier. We're gonna have, when we do the Bodie plot for this diff amp is gonna have some frequency response curve, and the common source is gonna have some frequency response curve, and there's gonna be different poles and zeros for the different transistors and everything. And we want to see what that compensation cap does. I can't say it yet. Okay. So here's my op amp, and I look at it, and I've got, and I just plot my poles and zeros. My first pole, no, I'm not frozen, thank goodness. I must have, let's see if this does me any good. Oh, wow, that does work. Amazing what you learn after a year. My first pole is right here. I've got a 0 right about here, and I've got a second pole pretty close to that. Now, the issue with this is if I look at this, okay, this 180 degree, you guys remember this, or if I babbled about this enough? If I want to build an oscillator, the way I build an oscillator is I have a circuit with gain, and I have a phase shift of 180 degrees, and I feed back the output to the input with a phase shift of 180 degrees. So the output adds to the input and makes it bigger. I parasitically start one little oscillation, and at one resonant frequency, this gets fed back, and it gets a little bigger, and it gets a little bigger. Every time you have a gain with a phase shift getting close to 180 degrees, and you have positive gain above 0 dB, it's amplified, you're going to end up with an oscillator. Okay, and it's not just that it has to be exactly 180 degrees. Controls engineers go a little bit nuts if you get close to 180 degrees because they want their systems to be stable. So they have this general kind of rule of thumb saying, I want the phase shift to be no greater than 120 degrees. And they call that 60 degrees of phase margin. I've got 60 degrees of safety before my thing goes into oscillation. That's actually minus 120. Minus 120. So if you look at this amplifier right here, where I get to that minus 120 point was the point where I've got the controls engineers nervous. I have gain less than 0 dB, but not a lot less. I potentially have an oscillatory system right here. I actually said that because of this. Now, if I could perform a magic trick that did this miraculous thing that made this go a little bit, make these two poles and make these poles and zeros split apart, I could get better stability. Now, old op amps, I haven't seen this on new op amps recently, used to have 2 pins on there for CC, and you could leave it open. If your amplifier started to oscillate, you put a little capacitor there and it would stop. And it's doing the same thing as this little capacitor is here in this network. It's feeding back and splitting the poles. The poles are too close. That's the problem. So what I do, if I put the CC capacitor here, it's between kind of like that gate to drain capacitor in the common source. It's going to kill, if I put a big capacitor there, it's going to kill my gain at an earlier frequency. And remember, we can split that capacitor into a much larger capacitor here. This one is like CC times the gain, times 1 minus K, but it's basically, if the gain's big, this is going to be times K. And I can put another capacitor here that's like CC divided by K, split it into 2 capacitors. So when I calculate the poles and the zeros for this, I get this much bigger capacitor here. So FP1, which is my dominating one, the CC, it goes in the denominator. So I'm doing math and talking engineering at the same time. This is amazing. Okay, I put the big CC, I put the CC here. So I put a big number here, it makes this one smaller. I'm gonna put a CC here, that's 0. It's gonna make that 0 go down to a lower frequency. And what does it do to this one? It gets multiplied. So this one gets bigger. It pulls the poles apart. So I'm not going to get the phase shift from the second pole. Okay, yeah, the whole story. I'm going to move this pole down. So the gain's going to roll off earlier. I'm going to have less gain before I get to where that original pole was. And not only that, but I move that other pole out, so I have even less gain when I get there. So I'm stabilizing my amplifier. And it's called a compensation cap. It kills the bandwidth, but it stabilizes your circuit. And a lot of op amps have that little compensation cap option on it. You see it on other circuits too. And that's basically what that's doing. Am I running out of time yet? Can we talk about the ADCs and DACs, right? Okay. Yeah, this is just doing the calculations. Okay, I think we're done. We made it through frequency response. See, part is we did so much more when I was in school.
Would you say it's still better to go into frequency response in 280 though?
What?
Would you say it's still better to go into frequency response in 280 though?
Yeah, because frequency, okay, it's like the 180.
We're not introducing the concept anymore.
We're not introducing the concept anymore.
I mean, like we reviewed it.
Oh yeah, in here. Yeah, yeah. In 280, it's bad because it's like I need to rewrite that. I think it was kind of like originally written by Dr. Brower to give you every possible combinations of zeros and poles and every crazy frequency response thing that you can. And it's almost become like 188ified. It's like finding the equivalent capacitance of this network of 20 capacitors that are going all over the place, or resistors or whatever. It's not really a useful exercise so much. It's more like just a mathematical exercise. And I think I need to like slim that down somewhat and make it more, this is a low pass filter and this is a high pass filter, and not worry so much about the analog filter stuff. And then maybe a band pass. I could completely go in there and do it, but every time I get to it, it's just like, I ain't good enough. I don't have the time. I just haven't had the time lately.
Well, I think the big thing is that, like, for some people, it's more intuitive.
Yeah.
When I first saw it, I was like, I don't know what's going on. But then once I started practicing it more, it would become just intuitive by itself.
Yeah.
So then that's when I could look at real life examples. I would be like, oh, that's easy.
Yeah, and sometimes having those gory practice problems is a good thing because it makes you get to that point.
Yeah.
Yeah.
Just feel it too.
Yeah.
You remember also from 280, you said if you want to build an oscillator, just try to build an op amp.
Build an amplifier. Yes, it is that's another fundamental law of engineering. If you want to build an oscillator, just try to build an amplifier. If you want to build an amplifier, try to build an oscillator. I had my first the first shot. Okay, what we were given when I got to Motorola was my first job out of college. Is the senior staff engineers had put together a schematic for a phone, and they said, okay, this should work. Theoretically, it should work. we're going to build a printed circuit board, and you guys have to make it work, all the engineers in there. And of course, it's an RF thing, and so there's all kind of parasitics and stuff that you need to worry about. And of course, it didn't work. But my amplifier at that point was a beautiful oscillator at every frequency between between like 60 hertz and 10 gigahertz.
Wow.
It was this beautiful oscillator. And every time I keyed that thing up to test it, to try to figure out what was going wrong, to try to fix this, the receiver person, who they unfortunately put in the cubicle next to mine, would scream because her measurements were just gone.
Oh, you should just do it as just put it down on the outside, or you see on the outside. Actually, that's the right amount.
Well, no, we had a time division multiplexing thing going on for a while. It's like, you're gonna do your receiver measurements for an hour, and I'll go off and work on something else, and then I'll key up my transmitter, and then you go off and work on something else. Because she could not make any measurements at all when that thing was on. Yeah. Mhm.
Or have technician would just be like, delete, delete,
Yeah.
delete.
And the oscillator was so touchy that to get it to oscillate, it just stopped working, and we were actually in production at this point, and it stopped working, and they shut down the line because the oscillator wouldn't work. We had the VP of engineering stomping up and down in Mike and Bang's cubicle, just make it work. Every hour that we spend not making phones, we're not making money or something like that. And so I'm helping him out, and everybody's helping him out. We're trying to figure this thing out, and he's getting so frustrated and everything that he's testing different values of components, trying to get that magic thing back. We got like a new reel of transistors in, and the whole thing didn't work. And so he accidentally solders one of the inductors in and the inductors are surface mount and have the leads coming out like that, and he accidentally solders it in upside down, and it worked beautifully. And we just want to get Ralph Peeney to stop jumping up and down. So what we ended up doing is for about a week there, until we could come up with a better fix, production went on, but there was a technician who was manually flipping the inductors upside down before they went through the wave soldering machine.
Oh my god.
But it calmed down Ralph Peeney.
True.
Yeah. People get highly emotional when you shut down the production line. Mm-hmm. Yeah. Everything else is forgivable. Yeah. Oh well. Okay. Any questions? Anybody I missed?
I didn't hear what you were saying.
Oh, I said any questions or anybody I missed. Let's take a look at this. I'm gonna just stop sharing so I can see my Victor, you are here. Alex, you are here.
Yeah, I'm here. I was getting a question answered, that's why I was late.
Oh, that's okay. I'm not worried about that. And Sigwy is here. Everybody's here. Okay. And it is the 8th. April 8th. 21. Something like that. Ah. No more questions. Okay. We'll go. Yes, we got through frequency response. Now we're on to ADCs and DACs.
So yeah, it was like 2 weeks.
2 weeks for that, and then we got a review for the final, so about a week and a half. Yeah. Yeah. And I've got to, there's other stuff I need to do too.